Hello. This this video will be about Brahmagupta's method for finding integer solutions to quadratics of the form dx squared plus 1 equals y squared. These are also known as Pell equations. To find these solutions, or to find more solutions, we will use this theorem, this method of Brahmagupta's. So if we consider the equation we're given, except we're going to make one little change, maybe we need to adjust this a 1 to some general b. If we can find a solution u naught v naught for additive c naught, which means replace here, replace this b, and another solution u1 v1 for additive C1, which means replace that with something else or possibly the same number, then this will be a solution for additive C0 times C1. So kind of the idea is if we have a solution, we can use it to generate more. Oftentimes, this solution and the second solution will actually just be the same solution, and we're composing it with itself here. So let's work a few examples using Brahmagupta's method. A couple things to note, Brahmagupta didn't have a proof or explanation of how he came up with all of this. It just worked, and all of his work that we've seen is correct and does work. So we're just going by example problems of his more so than an outline of a proof of why it worked. Mathematicians since have proved that it is indeed always correct, but Brahmagupta himself, at least through the writings we have, did not list a proof. All right, so let's start with this first one, 8x squared plus 1 equals y squared. This one, it's not too bad to just find a solution to start. If I let x equal 1, then we can think we have 8 times 1 squared plus 1 equals, well, that's a 9, which is a perfect square, which is sort of what we want to happen, right? We want that to have a perfect square over here for our y squared. So if x equals 1, we can say that then y is a 3. So 1, 3 is a solution. Now, they don't always come this easily. This one was just, I kind of noticed, if I let that be a 1, 8 plus 1 is 9, which is a perfect square. Let me find one pretty quickly. So I really don't have to do any tricks right here to adapt a wrong solution to find a correct solution, which is what we're going to do in a little bit with some other examples. So 1, 3 is a solution. I can generate more. Switch back to my pen. We can generate more using his composition that he did. So as a reminder, here's what we were looking for. The u naught v1 plus u1 v naught, then d times u naught u1 plus v naught v1. So you can kind of see here the u's and v's are mixed and added together. And over here, the d, which remember is the number with the x squared, the d is multiplied times the u's and then add the v's. That's kind of the pattern here. And it says a solution for additive c naught c1. And we can see in here our additive is 1. So when we compose this with itself, 1 times 1 is 1. So we'll have a solution for the original as well. All right, so let's generate more. We'll use 1, 3 composed with itself. So we'll have, remember it was the u's times the v, so it was the u times the v plus the other u times the other v. Your d, which was the 8 in this case, times your u's, so both of those are 1s, plus your v's multiplied together, so 3 times 3. So we can clean that up. What do we get? 3 plus 3 is 6, comma 17. So 617 is also a solution. And I can generate more. I can compose 617 with itself. I can compose 1, 3 with 617. I can generate as many as I want now that I have a solution. So there's one more solution. That's 1, 3 composed with itself. Let's do another one. Let's use 1, 3 and 6, 17. Let's use them both and create a new one. So remember, what did we do? It was the u times the other v plus, now switch the roles, so the 6 times 3. My d, which is 8, times my u's, so 1 and 6, plus my v's multiplied together, 3 times 17. And if I clean that up, what do I get? 18 and 17, 35, and what's 48, 99. And you can then check that in your original, check that in the 8x squared plus 1 equals y squared, and show that it is a solution. And so we found 3 solutions. One, because the numbers were kind of small and we were able to stumble across an answer pretty quickly. And then the other 2 by composing solutions together. I could keep doing this. I could compose, 617 with itself and find another solution. I could compose, these 2 together now. I could do the 1, 3 and the 3599. I could compose this with itself. But I can keep finding more solutions using this composition method. Okay, so that was sort of our not too difficult one because everything kind of turned out okay. And when I did these compositions, I ended up with integer solutions. I was able to find something with that 1 in place, the 8x squared plus 1 there. I was able to find a solution pretty quickly and kind of move forward. Let's see what happens maybe if that's not so straightforward. So let's look at this example, 33x squared plus 1 equals y squared. So this is a situation, I'm going to try something a little bit different. I'm going to look at 33x squared plus b equals y squared. And I'm sort of going to think, okay, I'm going to find a solution for this alternate situation. My additive isn't a 1 anymore, it's a b. I'm going to come up with a different number possibly to go there. I'm going to come up with a different solution and then hope I can alter it into a correct solution for additive 1. So looking at this, I kind of, in my mind, I'm thinking, well, I could let x equal 1, and that's 33 plus something. I need to be a square. So I could think, if x equals 1, then b could be a 3, because then 33 plus 3 is 36, which means y would be a 6, because it would be 6 squared would be at the end. So that's kind of my thoughts. So I can say, 1, 6 is a solution for, and now it's not an additive 1, we can say it's for additive 3. Okay, so 1, 6 is a solution if you replace that 1 with a 3. All right, so now what we're going to do is we're going to find another solution there and sort of try to alter it, if you will. All right, so let's compose this with itself. So 1, 6 composed, 1, 6 additive 3 composed with itself. So remember, it was the u times the v plus the other u times the other v, which matches here because we're composing with itself. The d value, which is a 33 here, times the u's, plus multiplying the v's together. So I know I went through that quick, but just you can flip back in your notes or flip back a couple slides, a little bit of time in the video, and you'll see that composition written down again. All right, so I get that. If we clean that up, we're going to end up with, 12 and 69. And that's a solution. Remember, it's a solution for not additive 3 anymore, of additive. Remember, we have to multiply those together. So 3 times 3, so 9. Okay, so kind of what that's saying, that's also saying like 33 x squared plus 9 equals y squared. It's a solution of that. Okay, so we're replacing it with a 9. But that's not what we want. We want a solution of 33x squared plus 1 equals y squared. So what I'm going to do is I'm going to take this 33x squared plus 9 plus, oops, not plus, equals y squared. And I'm going to divide it through by the 3 squared, by the 9, if you will. Notice kind of thinking ahead, this is going to cancel, and I'm going to sort of be back to this 1, which was my goal. Okay, so I'm going to clean this up kind of sneaky. I'm going to do 33, kind of rewriting my exponents. That's x over 3 squared, plus that's going to simplify to 1, 9 over 3 squared, equals, and this is going to be a y over 3 squared. So I see this new equation, 33 times x over 3 squared plus 1 equals y over 3 squared. Well, 12, 69 is a solution to that, right? Because I didn't change anything. I just divided everything through by 9. So if I let here, so like x was 12 and y was 69, so then x over 3, which is the new kind of replacement variable, if you will, is 4 and y is 23. And that's going to be a solution. So 423 is a solution for additive 1. There we go. Because what did we do? It is a solution to this new piece. We can kind of think, if you plug a 4 in here, or if you plug a 12 in, that's like plugging a 4 into that whole spot. Plug a 69 in, that's like a 23 in the whole place. So 4, 23 is a solution for additive 1. Okay. All right, so that one wasn't too bad. We kind of had to play around a little bit. We had to, what did we do? Well, we found a solution to a different thing, and then we realized we didn't want this 9 here, so we divided by through it. And dividing through by 9 sort of was like dividing my x and y by 3 because they got caught up here in that square. Okay, so that found me a new solution. And it was kind of nice because my new solution was an integer solution. And remember, when we're doing these, we're only looking for integer solutions. We're not looking for rational solutions or real solutions. We are strictly looking for integer solutions. Okay. All right, so let's do another one. So this one is sort of one of his, I guess, kind of like the classic example, one of the famous examples. If you tried to just do what we did on that very first example, just kind of fiddle around and find an x and a y that just happened to fit, it's going to be kind of hard because the numbers actually are the smallest answer, what we call like the fundamental answer, is actually pretty large. So it's going to be hard to just kind of fiddle around and find an answer. So we're going to use this Brahmagupta's method again, kind of like we did on that second example, where we're going to have to adjust. We're not going to be able to just go straight through. All right, so let's instead, kind of like what we did before, let's instead look at 92x squared plus b equals y squared, and we'll find an answer for some other additive b, and then we'll adjust from there. So let's find something that works. I'm going to sort of kind of keep up with that method. If x is 1, then I have 92 plus something needs to be a perfect square. Well, I could add 8. If I let b be 8, then 92 plus 8 is 100, which is a perfect square, so that says y is 10. So it looks like if I have x is 1, y is 10, that's going to work if I have an additive of 8. If I change that b to an 8, that will be a solution. But I've got to figure out how to, undo that. So let's try composing it with itself. So compose with itself and get another solution. So remember, it's 110 with additive 8. So it's going to be 1 times 10, remember, is the u times the v, plus the other u times the other v. So 1 times 10 plus 1 times 10, and then your d, so 92 times your u values, 1 times 1, plus now your v values, which would be 10 times 10. And then this is a solution and it's your two additives multiplied together. So 8 times 8, or 64. Okay. All right. So what does this end up being? 20, comma, 192. So is a solution for additive 64. So I guess what we're looking at, it's a solution for 92x squared plus 64 equals y squared. Okay, now that's not what we want. What's wrong with it? I've got a 64 where I wanted a 1. So I'm going to do that trick again from last time where I divide through by 64. But I'm going to divide through as 8 squared to kind of think about it that way. Divide through by 8 squared, divide through by 8 squared, and then sort of rewrite this as 92, kind of combine my squares, x over 8 squared, plus that's going to simplify to a 1, y over 8 squared. And so now what we see is I sort of have it back in the form of the original. 92 times something squared plus 1 equals something squared. So that was sort of my goal there. Okay, so what do I figure out that needs to go there? Well, originally, what worked was the x was 20 and the y was 192. So still x can be 20 and y is 192, but now for this new one, I need to divide by 8. So that tells me that my new x, I need to divide by the 20 by the 8. So I get what, 5 halves there. And then over here, the new y, it was 192 over 8, which ends up being what, 24? So my new y is 24. So what does that tell me? It says that 5 halves 24 is a solution for additive. And now what additive is it a solution for? Well, look up here. If I just kind of replace, instead of saying x over 8, if I just say this is something squared, that something could be 5 halves. This something could be 24, and it's now a solution for additive 1. So that's sort of my trick to get back to that additive 1. Now, this is a solution. However, it is not an integer solution. It is just a rational solution, right? 5 halves kind of puts me out of the integers. So what I want to do is I want to see, well, could I do something with it to get an integer solution? Now, this method I'm about to do is not always going to work to clear out a rational solution, but it sometimes does. And again, this method is not just a straightforward step-by-step algorithm that says this is the step you take every time and it will always work. It's more of a method. It's a fiddle around with it, play around with it, compose things with themselves, and just, try to see what can happen to get back to an integer solution. So I'm going to try composing it with itself, but let's make a note real quick here. But rational, not integer solution, right? That doesn't look like a frowny face. Let's erase it. Frowny face. Okay. So let's try composing it with itself and see just, what happens. So 524 is a solution for additive 1. So what did we get? We do our u's times our v's. So 5 halves times 24 plus 5 halves times 24. My d value is still that 92 times my u's. So 5 halves plus my v's multiplied times each other, 24 times 24, my bad. So when we clean all that up, multiply all that through, we get 120 and 1151 is a solution for additive 1, which is pretty awesome because what were we looking for? We wanted an integer solution to the original quadratic we were looking at, and 120 comma 1151 is an integer solution here. Now that we found one, that's kind of the ticket. Once you find one, you can generate a whole bunch more by composing with itself and then composing it with new ones as well. But so that's how we handle Brahmagupta's method.